Our New York-bound Concorde, Speedbird 3, is getting clearance to go supersonic.
Hello, good evening. It's Speedbird Concorde 3 with you. Flight level 280 to the Excel point.
Speedbird Concorde 3, good evening. After passing the Excel, you're cleared to accelerate and climb flight level 600.
Roger, at the Excel point, we are clear to climb and accelerate flight level 600, Speedbird Concorde 3.
To accelerate beyond the speed of sound, Mach 1, the afterburners, or reheats, are lit up 2 at a time.
Okay, 2 reheats, before, and then 2 more, please. Aboard.
The reheats are lit up in stages to reduce the impact of acceleration on the passengers.
Mach 1.
Mach 1.
And with the job done, the reheat is turned off again. Without the afterburners, Concorde's still gathering momentum, accelerating to her cruising speed of 1,300 miles an hour. She's the only supersonic aircraft that can fly at Mach 2, twice the speed of sound, without the continuous use of reheats. Concorde was also the first civil aircraft to use an electrical control system, the forerunner of the computerized fly-by-wire system introduced on the European Airbus. Concorde has hydraulic power control units, which are triggered from the control column by analog electrical signals instead of mechanical links. The systems may be 1970s vintage, but they're tried and tested, and they work. What makes Concorde special, though, is that unique shape and that delta wing, which curves in 3 dimensions, as Captain Lowe explains.
The delta wing is really a necessity of supersonic travel, and that really comes out of all the different designs that both the French and the British tried. It's not absolutely essential because obviously you see supersonic fighters with a different wing design, but for efficient and effective supersonic travel you do need the delta wing. That enables you to keep the airframe light, because you've obviously got to keep it as light as possible, also to contain the aerodynamics of both subsonic flight and supersonic flight.
But just how does the wing work over such a wide speed range? The secret is a characteristic the Delta shares with no other wing shape. It can fly slowly without stalling at very high angles of attack, thanks to an invisible force, vortex lift. All swept wings create vortices, or swells of air, at their tips. But on a Delta wing, as the angle of attack increases, the vortices spread, getting bigger and slower, eventually providing an airflow over the whole upper surface of the wing. Pull the nose up on Concorde, and those unseen vortexes generate more lift. Just look at that steep angle of attack at slow speed. That's why the droop nose is needed, to provide the crew with a proper view of takeoff and landing. Concorde doesn't have the conventional control surfaces of other aircraft. Instead of ailerons to control the roll, or elevators to control the pitch, there are trailing edge devices called elevons. Doing without a conventional tailplane, though, does create a problem. On all aircraft, as speed increases, the center of lift moves rearwards. Where other aircraft are trimmed using their tailplanes, Concorde gets around the problem in another way, using its fuel to balance the aircraft. Captain Lowe explains.
As Concorde goes faster and faster, what's called the center of lift moves back down the aeroplane. On subsonic aeroplanes, you just use normal control devices to get rid of this. But if we did that on Concorde, the drag that would be produced would be just far too great, and we couldn't fly as far and we couldn't fly efficiently. So to compensate for that movement of lift, we also move the center of gravity. That means we move about 10 tons of fuel from the front of the aeroplane to the back of the aeroplane. And we leave it there until we then have to move, descend, at which point we move the fuel forward, and we actually use most of it in the main tank.
At 60,000 feet, Concorde's traveling so fast, the friction of the passing air heats the outside surface of the fuselage to the temperature of boiling water. The hot metal expands. The aircraft actually grows 8 inches longer. Powering that speed are the Rolls-Royce Snecma Olympus engines, power plants originally designed by Bristol Siddeley in the late 1950s for military aviation. The Olympus was to have powered a British supersonic bomber, the TSR-2. Although this project was cancelled, the Bristol engineers continued to develop the design. It was the only engine available which could deliver the range of power Concorde needed. The Olympus had plenty of grunt at both ends of the speed scale, but two disadvantages. It dragged fuel by the ton, and at full throttle, it made the earth shake. Most of today's subsonic jet airliners have high bypass engines, where the air literally bypasses the hot core of the engine to emerge cool, slow, and comparatively quiet. The Olympus, on the other hand, is an out-and-out turbojet, designed to deliver sheer power, hot and fast, with the extra oomph of afterburner reheat to nudge Concorde through the sound barrier. But no jet engine, not even an Olympus, can swallow air at supersonic speed. So the air intakes on Concorde are specially designed to slow down the incoming air before it reaches the engine. During flight, hydraulic ramps control the incoming airflow. That helps slow and compress the air and ensures that however fast Concorde travels, the turbines don't have to cope with more incoming air than they can handle. The intakes and the turbine discs progressively compress the air until it's at 80 times normal pressure. In the combustion chamber, that compressed air is mixed with fuel and ignited. Before it leaves the engine, the hot exhaust can be fired a second time by afterburners to boost power. To cut noise at low speed, cold air is mixed in by devices called buckets, which also double as thrust reversers. Despite all that power and technology, for the passengers, flying on Concorde feels much like flying on any other airliner.
On one of the first flights at Mark II, a well-known politician went along with the designer. The politician said, "We're flying along here at twice the speed of sound. It's just like any other aeroplane." And the designer said, "Yes, that was the difficult part. We're flying along at 1,320 miles an hour, and we're in our shirt sleeves and blouses and drinking champagne in the case of the passengers. The only other aeroplanes that can be up here are jet fighter aeroplanes where the pilots are in bone domes and pressure suits." And it really was a superb technical achievement to allow us to, as Concorde crew and Concorde passengers, to sit here just like this.
After 2 decades, Concorde is still without a rival or a successor. But for how long?
Today's engineers could build a Concorde successor right now, but they couldn't build one which the world's airlines would be prepared to buy. Technology doesn't just have to produce something which is large and fast. They have to produce something which is large and fast and makes money.
And that's the problem. There are plenty of design ideas for new supersonic airliners, but they're still firmly pinned to the drawing board. Experts say a new supersonic airliner couldn't be developed until the year 2015 at the earliest. And as the world re-evaluates what progress really means, projects like HOTOL, an airliner come space shuttle, seem as permanently grounded as the wooden mock-up of Boeing's SST, which has found a final resting place in an American fundamentalist chapel. With the supersonic sky to itself, our Concorde is approaching New York. Time for Captain Lowe to throttle back to subsonic speed and begin the descent.
The aeroplane is turning now to a place called Kenda, and we're turning and altering our flight path so as to keep our sonic boom, which follows the aeroplane. It's always 20 miles either side of the aeroplane whilst we're supersonic. We're keeping that well clear of land, and our aim is to be subsonic by a position called Lind, which is now 76 miles away.
Slowing down brings the center of lift forwards, so that fuel transferred to the rear is now pumped forward again to keep the center of gravity at the right place.
So the ramps, the air intakes have now finished their job and have got to the fully up position. So we're now flying just like a conventional aeroplane, just passing through the sound barrier, passing through Mark 1, decelerating at this particular moment. And as you can see, there's no impact on the aeroplane whatsoever. We're still descending in a speed hold at 350 knots, still navigating on the inertial navigation systems. And I have the auto throttles in a standby mode, so as we begin to level out, and so the auto throttles will come into play and hold the speed.
As JFK Airport draws nearer, the crew get Concorde into the right shape and speed for landing.
270 knots, so we'll now take the nose and visor down. Gear down, landing check. Just now going to do the landing check, so I'm going to put the gear down.
Co-pilot Ken Snell has been flying the early part of the descent. He now hands the controls back to Captain Lowe.
See them, John? Okay, I have control. You have control. The lights, and I have the strobe, the runway.
The flight engineer calls out the readings from the radio altimeter.
50, 40, 30, 20, 15.
Touchdown for the main gear, but the nose wheel is still 17 feet above the runway, thanks to that high angle of attack. The control column is eased forward to get it down, and full reverse thrust comes on.
100 knots. 75.
Flight time to New York was 3 hours 22 minutes. Here it's 10 to 6, an hour and 10 minutes earlier than the time we took off.
Okay, we're now moving the nose back to its taxiing position and clearing the runway.
Just another working day for the incredible time machine.